Welcome. Today we will discuss the regression approach to ANOVA. You have gone through ANOVA, analysis of variance, one way analysis of variance, one way we will discuss in term with reference to one way analysis of variance, one way ANOVA. And the model we have given y I j, general model is mu plus tau y plus epsilon I j, that is for one way ANOVA. Okay. And here it is the general observation, and our data was something like this, that the factor or the treatment levels 1 to I to A levels, and this side the observations or replications to N, when we have gone for balanced one, and somewhere here if it is j, somewhere y I j is there, and this is the general model. So, how many parameters to be estimated? One is mu, another one is a number of tau y. So, total a plus 1 parameters to be estimated. So, in today's lecture we will see that how regression is used to estimate these a plus 1 parameters, and how the SSR, SSE and SST can be estimated using the regression approach. Further, what I will show you, I will show you one example, and then we will see that the ANOVA results versus our regression result for the model adequacy test. Okay, although the parameters level comparison also possible. So, essentially we will see that least square estimation of model parameters, the general regression significance test example, and few references. Let us see this model. What is the fixed effect one way model is y I j mu plus tau y plus epsilon I j. You require to estimate mu and tau y. So, what is the procedure in least square method? Least square procedure is you minimize the sum of squares errors, sum squares errors SSE. You minimize SSE. So, minimize SSE. Now, in this equation, what is epsilon I j is the error term, this is y I j minus mu minus tau I. Now, if I sum it over I and j, j equal to 1 to n, I equal to 1 to a, then you sum it j equal to 1 to n, I equal to 1 to a. But what we are saying, some square, that means you first make it square. So, this square and then sum it. So, this is your SSE, this is your SSE. So, we say this is the, if I denote that this is the function of L, L is this function, not function of L is denoted by this function. Then what you require to do? You require to find out del L by del mu and put it to 0, and del L by del tau I, then put it to 0, I equal to 1 to like a. So, what it will give you? It will give you one equation here and here a number of equation. So, you will be having a plus 1 number of equation, simultaneous equation, which to be solved. Okay. So, let us see the slides. What are the simultaneous equations? So, del L del mu given this is 0, and del L by del tau I given this is 0. So, the first one, if you take derivative of this with respect to mu, you will get this equation. Now, if you do the same with respect to tau I, you will get this equation. Okay. So, this equation and this equation here I equal to, so what, how many equations you have? You have a plus 1 equations, that is what we are seeing here. How this equation is coming, n mu on this, suppose you just think of this equation equal to 0. So, sum total of y I j across j and I will give you n mu, will give you this one y double dot, that is a grand total, and then mu here n times, n means the total number of observation. So, n equal to a n, that is n times mu cap, and for every tau there will be, how many observations are there? For every tau 1 n observation, tau 2 n observation, like tau I n observation, but for mu grand mean total observation is n equal to a into n. So, as a result when you put the number of observations into equation, then what happen? This will be n sum of all n y I j, which is nothing but y total. What is y total? Y dot dot. That is what we have computed earlier. So, let me repeat this case again. I have 1, 2 I a treatments, and you have 1, 2 j n your applications. Then if I write total here, this will give you y 1 total, y 2 total, y I total, y a total, and if you find out the grand total, this is y dot dot. Grand total is total of all those things. This is nothing but grand total means sum of j equal to 1 to n, I equal to 1 to I, y I j. Okay. So, what is our first equation? First equation is minus 2 I equal to 1 to a, j equal to 1 to n, y I j minus mu minus tau I equal to 0. Obviously, given that there tau I cap. So, in this equation, what I mean to say, if I remove the sum, this minus 2 will also be cancelled, then what will happen? If I write this portion, this is what? This was is n time total of y I j, that means y double dot bar. This portion gives you this. Now, minus this one, I equal to 1 to a, j equal to 1 to n capital, total is n times mu cap. Now, plus this, what is happening, tau 1 will be for small n times, because there are n observation. So, minus n tau 1 cap minus n tau 2 cap, like this, minus n tau a cap, this will become 0. This will become 0. So, then we are getting this equation, first equation, n mu cap plus n tau 1, n tau 2, like this small one, this is giving you this equation. Now, come to the second formula. What is the second formula? So, from this formula, first formula we are getting n mu cap plus n tau 1 cap, n tau 2 cap plus n tau a cap, this equal to y double dot. This is our equation number 1. From the second formula is, or equation is y j equal to 1 to n, then y I j minus plus mu cap minus tau I. This becomes 0. Suppose you are doing that minus this. Okay. So what is happening here then? This is minus. Okay. So using this equation, what you are getting? You are basically, suppose for here I equal to 1 to a. If I put I equal to 1, what I will get? This will go out. So it is n times mu cap plus what you will get here, this tau 1, that will also be n times tau 1 cap equal to y 1 dot, because this is the first row, this quantity will give you first row total. Okay. So in this manner, so you are getting first row total from the first equation, second equation, second row, this is. So you will be having such n a plus 1 least square normal equations. Okay. So what is the constraint here? Constraint is that if you sum up the a number of equations starting from the second one, starting from this one to the last one, that is a number of last two equations, if you sum up, you will get the first equation. So as a result, effectively you have unique a number of equations, but you have to estimate a plus 1 parameters. So as a result, what happened? You have a constraint. It is a over parameterized model. So you have a constraint that I equal to 100 tau I cap equal to 0, this constraint. Using this constraint, so what happened? And all these a plus 1 equation, you will be able to estimate the parameters. How? So what we got? We got n mu cap, small n tau 1 cap, small n tau 2 cap, like this, small n tau a cap equal to y dot dot, that is the total, grand total. Then this is nothing but n mu cap plus, if we take n common, this is tau 1 plus tau 2, all caps are there, plus tau a equal to y dot dot. This is nothing but n mu cap plus n sum of tau I cap I equal to 1 to a equal to y double dot. Now this is 0 because of the constraint. So we can write n mu cap equal to y double dot. Other way, mu cap is y double dot by n, that means grand total by total number of observations. This is nothing but y bar dot dot, and this is what we have done in ANOVA also. That is, what is the grand total average? This is from average formula, that sum of all observation divided by that total number of observations. So this is fantastic. Now if I take the second equation, this is my first equation, then second normal equation, this is n mu cap plus n tau 1 cap equal to y 1 dot, that is second one. Mu cap is known because already mu cap is estimated. So if I write now that means mu cap plus tau 1 cap equal to y 1 dot by n, this is nothing but y 1 dot average. So as a result, tau 1 cap is nothing but y 1 dot average, y 1 dot average minus mu cap equal to y 1 dot average minus y dot dot, that is average. Okay, y 1 dot bar, this average. So, this is what you have seen earlier also, that we said that for every row average, if you can recall, we found out that overall average and then the tau, then we found out the average here. This is 1 dot average, y 2 dot average, y I dot average, like y a dot average. Then we say that what is the effect of first level, that this average minus this average. What is the effect of ith level, y I average minus y, that this grand average. So, that means in general from this equation we can say tau I cap equal to y I dot, that is the average, ith average minus y this average. This is the estimate you have seen earlier. Now, now from here, from if I know the all the tau and mu estimates, then the residuals also will be known from the primary equations, y I j equal to mu plus tau I plus this. Okay. So, this is the rules. Now, for normal equation, that there are 3 rules. Rule 1 is, there is one normal equation for each parameter in the model to be estimated. So, we have in one factor and one way ANOVA, we have A levels for A treatment levels and grand mean. So, as a result A plus 1 parameters to be estimated, that I told you, I am repeating the same thing. So, that for every parameter there will be a normal equation, or A plus 1 equations will be there, and it is seen. Then the right hand side of any normal equation is just the sum of all observations that contain the parameter associated with that particular normal equation. See here, right hand side is what? Sum of all observations, because this is this equation with respect to mu, this is a equation, and right hand side sum of all parameters, sorry, sum of all observations, sum of all observations. Second one you see with respect to tau 1, sum of observations. So, like this. So, the right hand side of any normal equation is just sum of all observations that contain the parameter associated with that particular normal equation. Rule 3, the left hand side of any normal equation is sum of all the model parameters, where each parameter is multiplied by the number of times it appears in the total on the right hand side. You see, suppose you this one you consider, this one if you consider, you see that this is y 2 bar, it is n times the right hand left hand side, n times it appears for a particular row, number of n times the number of observations you got, n replication is there. So, these parameters in this equation, the parameters are multiplied by that number of observations, that is n. Okay. So, in the regression approach, you are finding that there will be as many equation as many parameters we have, and the general rule is that 3 rules are there. If you apply these 3 rules, you will be able to get all the equations, even if you do not go by the least square, the traditional mathematical procedure. Okay. Now, once you have the general equation, normal equations, you are in a position to estimate all the parameters, which are nothing but the way we have seen in one way ANOVA lecture. The same thing is coming, and it is obvious. Now, I will show you the important one, that is means that goodness of fit measures, goodness of fit, as well as I can say that the test, ANOVA test, overall test. So, what happened, we have seen that the ANOVA partitioned the total sum square total into sum square treatment plus sum square error. Now, using regression approach, how do you compute these things, SSE and SS treatment? If we say SS treatment, in regression you have seen, this is in ANOVA, one way ANOVA, and regression what you have seen that SST equal to SSR plus SSE. What is the SSR? Sum square regression. So, the sum square regression and sum square treatment. So, ultimately it is a partitioning the total variability into two parts. So, they will be almost same. Maybe because of the approach there will be some variability, some difference in the calculated values, maybe, but approach wise same. Though that means SSR here is nothing but equivalent to SS treatment. So, let us see then using ANOVA regression approach for how to compute that SSR, SSE, and we get the earlier results what we have already used. Okay. So, here we are using we will be using the concept of full model. Full model mean if ours is a one way ANOVA case, then Yij equal to mu plus tau I plus epsilon ij, that is full model. Another one is reduced model. Reduced model means suppose that this factor is not contributing in any way, then this model can be written like this, mu plus epsilon ij, when H0 that tau I equal to 0, I equal to 1 to a is true. It is true, then this model is nothing but this is reduced model. That means the treatments are not at all contributing to the response, or the independent variable in terms of regression is not contributing to the overall variability of the y, the response variable. So, we use these two and then we will apply certain rules to find out the sum squares for total, sum square for error, and sum square for treatment or regression. Let us see what is this rule. Rule is that the reduction in the unexplained variability is always the sum of the parameters estimates, in a sense that each multiplied by the right hand side of the normal equation that correspond to that parameter. For example, in a single factor experiment, the reduction, we have seen already the single factor experiment. Now, if we say the reduction is r mu tau, then this is basically how many parameters are there here? Mu and a number of tau, a plus 1 parameters. You see, each of the parameter estimates are multiplied by the right hand side value of the normal equation. So, what is the estimate of mu? That is mu cap. So, what is there in the right hand side of the normal equation? Grand total multiplied by grand total. What is the second one? Tau 1, right hand side y 1 total, like this, tau 2 cap y 2 total, tau a cap y a total. So, this is is equivalent to mu cap y double dot plus I equal to 1 to a tau I cap y I dot. So, this is what is the reduction of variability from of y, reduction of variability, that is if you use the full model. Okay. Now, if we assume that from SS sum square point of view, that means the sum square of all the observations, we are not talking about sum square deviation, sum square of all the observation j equal to 1 to n, I equal to 1 to a, and if this is subtracted by r mu and tau, What is this? This is what is the reduction of variability if the ANOVA model is used. Then the difference is giving you sum square errors. That means this is the variability in y, and this one is here mu is included. So, this one is the variability including mu, means what I mean to say y I j equal to mu plus tau I plus epsilon I j. I am taking square of this, suppose, then and this one ultimately we want this. So, y I j equal to epsilon I j equal to y I j minus mu minus tau I. So, that sense if I square this and then take the sum, you will get this, and this one is coming here, and what about this? This is what is the model part. So, this model part is coming here. Now, you understand. So, as a result we are saying this is SSE. Okay. Now, then what about this R, mu and tau? That is, we said that mu cap y double dot plus sum of tau I cap y I dot I equal to 1 to a. So, if you expand this, you will get this one. You see what you are getting. If you expand this, you are getting this mu I cap is nothing but y grand average into this and into this, and if you expand this, you will be getting that is nothing but y I dot square by n, I equal to 1 to a y I dot square by capital small n. And square by small n. Now, that means if I put in SSE, then this is nothing but j equal to 1 to n, I equal to 1 to a y I j square minus sum of I dot square by n. Okay. So, so this is your SSE. Now, this you are getting from the full model. Now, if we do the same thing from the for the reduced model mu plus epsilon I j, then epsilon I j is what? Y I j minus mu. If you take square, you make square it and sum of this, then SSE what happened you will get from here. But rather we are interested in this R, we are interested only R mu. Here mu and tau, because for the full model, and here this, what is the procedure? Multiplied by, so estimate is mu cap multiplied by its total. Now, this will give you y dot dot square by capital N. You may multiply, do this, you will get this. So, as a result what happened now if I want to know what is the R value of the x factor, that factor one factor given mu, what will happen then? This is nothing but R mu tau minus R mu. So, that means R of full model minus R of reduced model. So, what you got in R of full model? We have already seen this is y I dot square by n, I equal to 1 to a minus what is the R of reduced model? This square by n. What is this value? This is nothing but the treatment of contribution, sum square treatments, sum square R, SSR. Okay. So, anyhow, using all those things, now what happened? You got SSE using this formula, you are getting the that factor contribution or SSR or SS treatment by this formula 1 by n of this formula. So, I think what I have done here, okay. So, this okay 1 I by n is there, fine, 1 by n of this formula. Then you can find out that f0 value is what? F0 value is our SS treatment by degree of freedom by SS error by degree of freedom from ANOVA point of view. From regression point of view, SS bar by degree of freedom by SSE by degree of freedom. This is nothing but now SS bar is here R tau given mu divided by A minus 1, and then SSE already you know the formula is given to you. So, I am not writing here further SSE by n minus A. Now, if this follows same thing A n minus A and rest of the things known to you. So, very quickly I will show you that in ANOVA for the power each rate data we have seen SST is 72,000 almost, treatment 66, SS error is 553 like this, and then this is the ANOVA table, and we found out that there is treatment effects. Now, we have used the same thing for regression. What we have done, there are 20 observations, then x value for first observation 200, 220 like this, then y values are there, then regression model is fit, then y credited sum square everything. Now, SST is 72,209.75, here 209.75. Then SSE is 8352.46, but here it is less. So, maybe that is because of the rounding error and other things may be there, but whatever may be the thing, but ultimately total is same, and then the predicted values we have taken for 2 decimal. So, the error is also for 2 decimal, maybe that may be the effect, or maybe the approach, from the approach also there is little different values. And then what happened, we found out that from regression also the F statistics is very high, and we are saying that it is significant. So, from ANOVA as well as from regression both case you are finding that the power has effect on the each rate. Okay. So, any one way you can go, but please keep in mind here the degree of freedom is number of parameters to be estimated minus 1. So, intercept plus the model regression coefficient for power only, so 2 minus 1, and then residual is more, and that is basically this. So, that is MAC is 464. Now, what about MAC here? 330, 333. Okay. So, find out, if you can find out that there is there may be calculation error, please tell me in the forum, and or if you find out that no, that there is even further or much closer explanation for the two, also discuss. It is all those things are welcome. Thank you very much for your patient hearing.